Let's talk about electrons. Today we're going to talk about the Bohr model, quantum theory, and electron configuration. But before we do that, we got to remind ourselves a little bit about atomic theory. Remember that back when we first learned about the history of atomic theory, we learned that Rutherford and Chadwick developed their atomic model, their nuclear model of the atom, after doing the gold foil experiment, discovering the nucleus and the proton and the neutron and all of that. What they could not do, though, is explain some of the behavior of atoms that we were discovering, something called atomic emission spectra. Atomic emission spectra is the way that atoms give off light. We're going to talk about that more in a couple of days, and we're going to do a really cool experiment with that. But we're going to discuss that a little bit later. So to help explain this atomic emission spectra, Niels Bohr developed his quantum energy model of electrons. So he did this and he called it his quantum model. So that fun little word quantum is a fancy word that means something has a smallest possible value, and you can only move from one value to the next by a certain amount. You can't have pieces in between. It's either this or it's this. That's what quantum means. Something is quantized, you have a certain amount. So a good example of that is US currency, the money that we use to pay for things. If you go to the store and you're going to buy something, everything, the smallest piece of money that you can have in your pocket is a penny. You can have 1 cent. You can't have 1.2 cents. You can have 1 cent, or you can have 2 cents, or you can have 3 cents. You can't have 1.675 cents. So the smallest piece of currency in our country is a penny. You can only move up and down by 1 penny at a time, 1 penny increments. So that means a penny is a quantum of money. So that's what it means to be quantized. Our money is quantized. You can have 1 penny, you can have 2 pennies. And that's the way our currency system is set up. So that is what we mean by quantized. So when Bohr said that electron energy was quantized, what he meant is that the energy of an electron had to exist in defined amounts. It could either be this amount or this amount or this amount, but it couldn't be anything in between. It had defined amounts of energy. That's what he meant by the energy being quantized. And that's why he called it the quantum energy model. Now, he called these energy levels the amounts of energy that they had. So they had the first energy level, the second energy level. We used to call them the principal energy levels. Some people still call them the principal energy levels. So we just have the energy levels, or these shells, as we learn them now. So he hypothesized and just thought about it that electrons would orbit the nucleus in circular orbits, much like the planets orbit the sun, and that the energy of the electron was determined by which orbit it was in. Lower energy was closer to the nucleus, higher energy was farther away from the nucleus, and it's orbited like the planets. Now, each energy level or energy shell could only hold a certain number of electrons. So when you're closer to the nucleus, it could only contain a small number of electrons. And as you got farther away from the nucleus, you could contain more. One, because the energy level was larger, so there was more quote unquote room for electrons, but also their energies wouldn't compete with each other. So we have these energy levels. So we call them N. We use an N to represent the energy level. So the first energy level, Bohr figured out, could only hold 2 electrons. And the second energy level could hold 8 electrons. So if you had 3 electrons, 2 of them would be in the first energy level, and the third one would have to be in the second energy level. And then if you got up to 10 electrons, you could have 2 in the first and 8 in the second. But if you added an 11th electron, like your sodium, and you add an 11th electron, then that 11th electron now has to go to the third energy level, because the second energy level could only hold 8. The third energy level could then hold 18 electrons. And the 4th, 5th, 6th, and 7th energy levels, as represented by the elements on the periodic table, can hold 32. We will discuss in a little bit the reason for these numbers that we know now. Bohr didn't understand or know why these numbers were what they were. This is just the way it worked out in his math. And these were the experiments that he did. This is how he figured it out. But he didn't know the why. We now know more or less the why these numbers are what they are, as we're going to discuss in a little bit. So What we're going to learn about now, though, is how to draw a Bohr model diagram. There's a way of modeling the electrons using Bohr's method to model it. It's very simplistic. It's not completely accurate when it comes to how atoms and electrons actually exist, but it's a good understanding, basic understanding of electrons and atoms. That's why we're talking about it right now. It was a first understanding. We know better now. And so we're going to talk about how to draw a Bohr model diagram. All right, so now we're going to look at how to draw these Bohr diagrams. So first thing I'm going to do is I'm going to pick an element. Just going to pick any element. Let's say I want to do iron. Okay, so we're going to draw the Bohr model diagram for iron. So to do that, first I have iron, and iron has, sorry, let me put this back. Iron has 26 electrons. We know it has 26 because the atom has the same number of electrons as protons. It's not an ion. We're dealing with the iron atom. So the proton number and the electron number are the same. It's element number 26, so therefore it has 26 electrons. So we know that we have 26 electrons to deal with. So what we're going to do when we do our Bohr model, the way we're going to do these in the class, is you're going to have something to represent the nucleus. Sometimes you'll just have a black dot. Oftentimes the way I do it is I write the symbol for the element as the nucleus. So this represents the nucleus of iron, the 26 protons and however many, 25, 27 neutrons that it has. This is the nucleus of our iron. So then what I'm going to do is I'm going to draw an energy level around it. So this is our first energy level. Now, as we just learned, the Bohr model tells us that the first energy level can hold 2 electrons. So I'm going to draw 2 electrons on there. Now, electrons are both negative. They're going to spread apart. They're going to push each other away, so draw them opposite each other. It doesn't really matter which side you draw that on. We just draw them opposite of each other. So we have our 2 electrons. So I had 26 to deal with. I just used 2 of them, which means I now have 24 electrons left. Now the first energy level can only hold 2 electrons. So now I have to move on to the second energy level. So I draw another circle. Your circles don't have to be perfect, but hey. So the second energy level can hold 2. The first energy level holds 2. The second energy level can hold 8 electrons. So I'm going to draw 1, 2, 3, 4, 5, 6, 7, 8. So I have my 8 electrons there. So I've just used 8 more electrons. I now have 16 left to place. So I used 2 and then 8. So that's a total of 10. Started with 26. So I've used up 10 of my 24 electrons. So I need to place 16. Now the second energy level can't hold any more than that. It can only hold the 8 electrons that I already have. So now I'm going to go on to the third energy level. All right. Well, the third energy level can hold 18 electrons. I have 16, so I can place all 16 of them here on the third energy level. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I placed all 16 of them on there, and so I've used up all 16, so I now have 0 electrons left. So this is our Bohr model diagram. Now, this is not 100% accurate. In fact, if you look at the periodic table, you notice that iron is in the 4th period, and we already talked about how the period represented the energy levels. There's a reason for this. We will discuss that in a later video, but you do need to know that the Bohr model is not a perfect way of understanding how electrons go, but this is how we're going to draw it for this class. So the Bohr model is not perfect, and we are going to learn different and better ways. This is a simplistic and easy way of representing the electrons and atoms, and this was one of the first understandings of electrons and atoms, and so that's why we're moving on with that. So that is our example of the Bohr model. Let's get back to talking about quantum theory and all of that. Okay, so now that we've learned about the Bohr model and how to draw the Bohr model diagrams, now we're going to discuss what came from that, what came after that, the quantum mechanical model. All right. Bohr's model could really only explain the behavior of the electrons in hydrogen. That's really all he worked with. That's all he worked with because it got to be too complicated mathematically for all of the others to look at every single little electron. It became very complicated. So Bohr's model could really only explain the behavior of electrons in hydrogen. Well, that's one of the now 118 elements that we have. So that doesn't really help us solve the problem of describing how electrons behave in atoms if we can really only accurately explain one element. So along comes Erwin Schrödinger. And Schrödinger developed a better understanding, and it's more or less our current understanding of how electrons behave by treating electrons as waves instead of particles. Instead of treating them like particles, like planets circling the orbit, he treated them like energy waves surrounding the nucleus, right? And by treating them as waves, he was able to figure out a whole lot more about the way the electrons behave that actually match what we see in nature and we see how things behave. So that's one thing you really need to understand is that when scientists hypothesize and they model things mathematically, we then take that mathematical model and see if it compares equally or matches what we actually observe in nature. And we found that Schrödinger's equation did actually fit what we observed, and it explained our observations that we found about atoms in nature. And so that's why we still use it today. So Schrödinger's equation gave us what we call electron orbitals. Right? And what an orbital is basically an area of space where the electrons are most likely to be, where you're most likely to find an electron. So they don't form perfect circles that orbit around the nucleus. They don't do that. They fly all over the place randomly. It appears randomly. And so what Schrödinger's equation does is gives us a probability of where is this electron going to be with this amount of energy in this particular situation, where is it most likely to be? So that will tell us the general region where it's going to be. So for example, if I wanted to know where are you? Well, at the time of day that you're sitting in my class, you are most likely going to be in my classroom. Now, you might be walking down the hallway, going to the bathroom. You might have gone to get a drink. You might not be in class that day, but on a given day of class, whenever you're in my class, there's a high likelihood that you are sitting in my class period. So the area that my classroom is where you're most likely to be during class. Do I know exactly where in the class you are at any given instant? No, but I have a pretty good idea of where you are. That's what Schrödinger's equation does with the electrons, is it gives us a probability of where the electron is most likely going to be at any given moment. And so with that, we can draw an area, a region, a shape. These are three-dimensional shapes that tell us where the electron is going to be. All right. So these orbitals have specific shapes. Now, again, when we say they have shapes, we can't actually see them. It's not like you're going to look at an electron and you're going to see a shape. So we draw these, but this is basically, if I were to draw a line around the area where the electron is most likely going to be, this would cover it. Okay. So that's what these shapes are. So there's 4 orbitals here. So we've got the s orbital is basically a spherical shape. So the s orbital is a spherical shape. You can see that here on the thing. So you've got your X, Y, and Z Cartesian axes that you learn about in geometry. And so we've got our sphere, and the quantum model of the s orbital is a sphere. We have the p orbital is made up of 3 suborbitals. So the p orbital is made up of the 3 parts, and each of those parts are shaped like peanuts that lie on the 3 spatial axes. So they lie on the x-axis, the y-axis, or the z-axis. Now, I'm giving these things shapes that the name of the shape matches the letter that we use for the orbital to help you remember the shapes better. So the s orbital is a sphere. I could have said a ball, but it's a sphere. The p orbital is a peanut shape because peanut starts with a P. That's why I'm using those letters. So the p orbital, though, has these 3 suborbitals, 3 parts to it. And then you have the d orbital, and the d orbital is made up of 5 suborbitals, each with a double dumbbell shape. All right. I'm, again, using letters, names of shapes that have the letter of the orbital in them to make it easier to remember. So this double dumbbell shape here is kind of a weird way of doing it. And this, of course, one in the middle is not a dumbbell at all. But when you see these pictures, you should see, oh, hey, look, it's double dumbbell. So it's a d orbital, double dumbbell d. So that is the d orbital. And then we have the f orbital, which is made up of 7 suborbitals, and they're shaped kind of like flowers. I mean, this is what a flower looks like whenever a 2-year-old draws it. At least my 2-year-old, when she scribbles a flower, it looks like a whole bunch of little crazy things. So you've got a funky flower, you've got a double dumbbell, you've got peanuts, and you've got a sphere, S, P, D, and F. If you remember our discussion of the periodic table, we had the blocks of the periodic table were the S, P, D, and F block. That will come into play in a little bit. So we will understand how that works. So these are our orbitals. Make sure you understand and know these shapes. Now, each suborbital can hold 2 electrons. So you'll notice the S, the P, the D, the F, those are the orbitals, and then there were suborbitals within them. And each suborbital can hold 2 electrons. So let's talk about that a second. The S orbital has 1 suborbital. So there's not a suborbital, it's just the s orbital is a sphere. And so it can hold 2 electrons. The p orbital has 3 suborbitals, and each of those 3 suborbitals can hold 2 electrons. So 3 times 2 is 6. So the p orbital can hold 6 electrons. The d orbital has 5 suborbitals, and therefore can hold 10 electrons. 5 times 2 is 10. Each suborbital holds 2 electrons. And the f orbital has 7 suborbitals and therefore can hold 14 electrons. So again, 2 times 7 is 14. So these are the maximum number of electrons that these orbitals can hold. That's not how many they always have. It's just the maximum number that they can have. If you have more than 14, then you're going to have to go to a different energy level or a different orbital. So the quantum mechanical model continues to tell us some stuff. So the Offball Principle is an understanding, I'm going to go into some vocabulary here. The Offball Principle basically tells us that electrons will fill the lowest energy orbital before filling higher energy orbitals. It's going to fill the lowest energy first. So, for example, let's say you are really, really tired after a long practice, your legs are beat, you're hurt, you don't want to walk any farther, and you walk into my class, and the last thing you want to do is walk all the way to the back of the classroom to sit down. So you're going to walk in and you're going to sit at the first seat possible, assuming we don't have assigned seats. And you just walk in, you're going to sit in the first seat that you possibly can because your legs are tired and you don't want to walk anymore. And so you walk in, you sit in the first one because you don't have any energy. When someone else comes in behind you who's in the same boat, that seat's already taken, so they're going to sit in the next closest seat. And that's the way electrons fill electron orbitals. They fill the lowest energy possible first. That's the Offball Principle. All right, we have this little diagram here, and you'll notice as you look at this diagram that we have all these different orbitals, and I'll talk more about these in a minute, but this is the order that they fill. And so they fill one at a time. This is the order of the energy. And so hopefully you'll see how that works in a bit. Okay, when you're filling the orbitals, electrons have what is called a magnetic spin. Okay, we say that spin is either up or down. It has to do with the way the electron produces a slight magnetic field, and so it's an up or down spin. The thing is you can't have 2 electrons with the same spin in the same suborbital. They don't work that way. So that leads us to Hund's rule. right? Electrons with the same spin must fill each suborbital before electrons with opposite spins could fill the same orbital. So what that means is, let's say that you're going off to college and you're going to go into your dorm and you're going to go potluck, and it's just you go in and you get to pick where you're going to be and who your roommates are going to be. This isn't the way it actually works, but let's just say that you get to pick. Well, most people, if given the opportunity, would have a room by themselves. So everybody's going to walk in, they're going to pick, well, that's going to be my room, that's going to be my room, that's going to be my room. Each person picks a room by themselves. But not until all the rooms are filled do people start pairing off and having roommates. That's the way electrons work, right? So when it comes into the p orbital that's on the x-axis, that we'll call it the px orbital, that suborbital, if it has an electron in it, then the next electron is going to go to the py orbital, that other suborbital. And the next electron is going to go to the pz suborbital. So you'll have the three suborbitals all get one electron before any of them get two, because they don't want to share unless they have to, right? So they're going to fill up all of the orbitals first, and when they're all going to have the same spin, and then you're going to have ones with an opposite spin that will share with them. That's Hund's rule. The Heisenberg uncertainty principle is another vocab word that you need to understand and that you need to know. Basically says we can either know the speed and the direction of an electron or its position at any given moment, not both. And we can't know exactly where it is and how fast it's moving at the same time. And the reason is because in order to measure where it is, we have to change how fast it's moving by hitting it with something. In order to know how fast it's moving, we have to know where it is. So we cannot know both at the same time. That's the Heisenberg uncertainty principle. It's a little more complicated than that, but that's basically it for what we need to do in this. So quantum numbers of an electron are like its address. They tell you the energy level, the orbital, and the spin of the electrons. They tell you where it is and what its spin is, how you can fit it, okay? So the Pauli exclusionary principle deals with these quantum numbers. We're not going to get into what the quantum numbers are right now and how to do that and how to figure out the quantum numbers of something that's not necessary for this class. But you do need to know that electrons will have quantum numbers. And what Pauli exclusionary principle tells us is that only two electrons can occupy the same suborbital and they must have different magnetic spin. What that tells us is that no two electrons in an atom can have the same set of quantum numbers. No two people can have the same address, all right? Two electrons in an atom cannot have the same set of quantum numbers. So this atom and that atom can have electrons with the same set of quantum numbers. But this atom right here, all the electrons in this atom must have different set of quantum numbers. That's basically what Pauli exclusion principle tells us, all right? So how do we define where these electrons are? It's something called electron configuration. So it's how we write out where the electrons are located. Electron configuration shows us where all the electrons are located in an atom. So right now I'm going to show you how that is done and how we would write that out.
All right, so to do this electron configuration, the first thing that you need to know is how we write it down. We need to write the terms. So when I say a term of your electron configuration is going to consist of three things. You're going to have a number that represents the energy level. So 1, 2, 3, 4, 5, 6, or 7. So you're going to have a number that represents the energy level. You're then going to have a letter that represents the orbital, S, P, D, or F. So let's say we're going to use the D orbital here. So this would be, I'm talking about the electrons in the third energy level in the D orbital. And then we're going to have an exponent, a number written up here at the top. We're going to have an exponent that's going to tell us how many electrons are in that orbital. So the third energy level, D orbital, let's say it has 7 electrons. So this would be the term 3d7. So when we're writing out the full electron configuration for a element, we're going to tell where all of the electrons are in all the terms. So when you do it correctly, the exponents should all add up to your total number of electrons. So this is what we mean by a term. So now let's talk about how we're going to actually do that electron configuration. And we're going to do it because we're going to tell where all the electrons are, and we're going to do it in order of the lowest energy level. We're going to follow the Offball Principle. And remember from just a minute ago, those notes had the picture of the Offball diagram. And this shows the order that these orbitals will fill by energy level, lowest energy. All right, so as you go through it, it's 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. So you'll notice the 4s gets filled before the 3d because the 3d orbital actually has slightly more energy than the 4s, and they always fill the lowest energy possible first. And the 3D has slightly more energy, even though it's the third energy level. And this is actually part of the reason why that Bohr model that we drew a little while ago, why the iron didn't seem to fit what it said on the periodic table. And this is why the Bohr model is not 100% correct. And so we're going to get into that a little bit more later. So this is the sequence. So I'm going to use this sequence in order to draw the electron configuration. So let me just show you how to do that using an example. And we're going to use the example of polonium. Now, polonium has 84 electrons. And so we're going to have to tell where all 84 of those electrons go by using the terms that we just talked about. So we're going to start with the first term. And the first term is 1s. So I'm going to write 1s, and an s orbital has or can hold a maximum of 2 electrons. So that's 1s2. So then after 1s, we come to 2s. So I write my next term, 2s. In it, again, is an s orbital. It has 2 electrons. All right? So then I go to the next one, 2p. Still the second energy level. Now I'm in the p orbital, and a p orbital holds 6 electrons. So it's 2p6. Okay, so right now I've done 2, 4, 6. That's 10 electrons. So I've used 10, so I have 74 left to place. Okay, so after 2p, I continue following the sequence, is 3s. So now I have 3s, and again, an s orbital holds 2 electrons. So 3s, 2, and then 3p. This is not super complicated yet. So 3p, again, a p orbital holds 6 electrons. So I've gone there. Now the next one following the arrows is 4s. So I write 4s, and an s holds 2. Now let's tally up. I've tallied those, so now I have another 10 that I've just used. 2 and 6 is 8 plus 2 is 10. So now I'm at 64 electrons that I have used. Okay, so now I'm going to go to 3d is the next one. So now 3d, now a d orbital has those 5 suborbitals with 2 electrons each, so a d orbital holds 10 electrons. So 3d10. And now I go to 4p, and 4p holds 6, and then I go 5s, and an s orbital holds 2. So I've just used another 10 and 6, and 2 is 18. So I've just used another 18, and so I now have 46 electrons left. I've used, I've just subtracted 18 from that. So to show you what I was doing here, I subtracted 10, subtracted 10, subtracted 18, and now I've got 46 electrons left to place. Okay, so now I'm running out of room, so I am going to come down to the next line. After 5s, though, the next thing is 4d. So I'm going to come to my 4d, and a d orbital holds 10. Okay, so after 4d, I do 5p. So 5p is 6. So I've just used another 16 electrons. So I subtract another 16 electrons. I am down to 30 electrons left to place. Okay. And I just did 5p. So looking back at our sequence, 5p, the next thing is 6s. So I do 6s, and an s orbital again holds 2 electrons. All right, and after 6s comes 4f, okay, and 4f. Now an f orbital has 7 suborbitals. Each one holds 2 electrons, so an f orbital holds 14. So I just used another 16. So 30 minus 16 is 14. So I have 14 electrons left to place. And I was just here at 4f. So the next one is 5d. So I write 5d. D orbital holds 10. All right, so I've just used 10. So I now only have 4 electrons left to place. And the next spot after 5d is 6p. And so 6p, and even though a p orbital can hold 6, I only have 4 electrons left. So I can't put a 6 there. If I wrote a 6 here, that would be wrong, because that would say I have 86 electrons when I only have 84 to start off with. Okay, so 6p, I only have 4 electrons left, so this has to be a 4.
So now that you've seen the long drawn out electron configuration, the full complete electron configuration for one atom, and I chose a big atom so that it would take a while and you could see how that worked. In our next video, we're going to learn how to write that in a shortened condensed form, and what we're going to do with all these valence electrons that we were talking about before, the ones that are really important, all right? Because we talked about how all of these electrons are important and where they're located, but the ones that matter the most to us are those valence electrons. That's what we're going to talk about in the next video, how to do this electron configuration in a slightly shorter way, and what do we do with those valence electrons. So thanks for watching and have a day.